so today you're pleased to have Donggyu Kim, who used to be here. But, anyway, we'll talk about even delta matrix, right?
Yes.
Please.
Yes. Thank you for having me here, and it's very glad to back home. Okay, so today I will talk about about the even delta method, and I will not most talk about orthogonal method, but basically those are the same concept. So yeah, this is joint work with Changxin Ding, and it was began at the early of the 2024, but it is almost finished. Yeah. Okay, let's start with some basic fact about the linear algebra. I think most of you, maybe all of you, know about the Cayley's theorem. This theorem about the Pfaffian identity. So we have some skew-symmetric matrix. And then the Cayley's identity implies that the determinant of A is equal to Pfaffian square. By the way, is there anyone who do not know about the definition of the Pfaffian? Okay, so let's try to remind you the definition of the Pfaffian first.
They didn't know, so it's not reminded.
So basically, Pfaffian determinant is defined using the what? All possible permutation, and you may understand permutation as some kind of cycles and edges in the complete graph. And rather than that, Pfaffian can be understood in terms of the perfect matchings. So, okay, so you may consider some complete graph with some edge label, which are edge labeled complete graph, and so you may consider some A is equal to Aij, and those Aij's are the edges of our complete graph. And you may consider some labels. You may consider some linear ordering of the vertices. And the Pfaffian of A is enumeration of the all possible way sums of the perfect matchings. What I mean is this is summation of the all perfect matchings. So something like so what I mean is A, I, and some sigma I. So you may consider some kind of specific permutation, which is has no fixed point and which is involutive. So with this, which corresponding to the perfect matchings in the complete graph when this N is given. And so by this is so sigma is perfect matching. What I mean is no permutation which does not have a fixed point, and which is involutive, and then taking the all product of those rays and with some suitable choice of the sign, which determines by the number of the crossings of this perfect matching. And this is just definition of the Pfaffian. And you may understand determinant as in terms of all possible permutation. And if you have some kind of perfect matching, and then if you have two perfect matching, and you may consider this as by using some kind of alternative path argument and so on, you may consider the two perfect matching as some kind of unions of some kind of cycles and so on. So using those kind of argument combinatorially, you can put this identity. Okay, let's keep in mind, and those are the very well-known result. But by the way, indeed, he proved a little bit general theorem.
Wait, by skew-symmetric, do you mean that Aij is equal to a negative Aji?
Yes. And the diagonals are equal to 0. So you may consider this over any kind of field, but so and characteristic 2 field, and you need also additional assumption about the diagonals are equal to 0. Okay, so yeah, so what it means is Aij is equal to negative Ji, and Aii. And yeah, Pfaffian is not well defined when our matrix is not skew-symmetric. And okay, let's go a little bit further. So let's fix some I and J from our ground set 1 through n. And let's denote A super I. Let me see. A super I sub J is the submatrix of the our matrix, given matrix A, by deleting i's column and the j's row, okay, which is just n minus 1 by n minus 1 submatrix. And what Cayley proved that determinant of the A also can be written in terms of the Pfaffian of our original matrix A. More precisely, it can be written in the following form. So it depending on the parity of n. When n is even, this means that there's some indicator function of with respect to this logical statement. So this is 1 when I is equal to 1, I is larger than j, and 0 otherwise. So by definition, Pfaffian is always zero when this is Pfaffian of the odd size symmetric matrix, skew-symmetric matrix, and in respect to those conditions, this Aij, A, and Aii, and Ajj is always the even-sized skew-symmetric matrix. So yeah, this is quite proof of this is still quite easy, just using some kind of very inductive argument. But this is less well known.
So what is this? So I have trouble understanding the notation. What did you write? Aii?
So Aii, mean that deleting i's rows and i's column, and Ajj deleting j's and rows.
What about the previous line?
This line is deleting ij's, two lines, ij and ij's.
Oh,
yeah.
I see. I see. I see.
Okay. I will try to write make a better handwriting. Okay.
Is there anything about, so it's just arbitrary I and j, or is it?
This is for arbitrary I and j,
Arbitrary.
which when those are distinct. So basically, this is some kind of, sometimes this is called almost principal minor, because this is, when this is I and j's are equal, then this is still skew-symmetric, right? But when those I and j are not equal, then this is not principal minor, but looks almost like skew-symmetric, and which is called the almost principal minor of our original skew-symmetric matrix. Okay, so please keep in mind those things, and let's go a little bit further algebraic. So I will denote one notion, which is orthogonal Grassmannian. Don't be worried about that. I will just give you some kind of, this is nothing but just set of the sum vector spaces. You know that Grassmannian is set of the some linear vector spaces, and this is set of the some specific linear vector spaces. And I will definitely go further, but let's begin with those just definitions. So this is the set of the all maximal isotropic subspaces, linear subspaces in C to n dimensional space. And here I will denote is coordinate with the 1 star, 2 star, and so on, n and n star. Okay. And here isotropic means that this vanishes with respect to the following symmetric bilinear form. So here, isotropic, some vector space V is isotropic. Means for all x and y in V, this symmetric bilinear form is vanished, which is defined in the following way. So this is summation of the all those things: x, I, y, I star plus x, I star, y, I. And this is when this vanishes for all choice of the x and y, then we call our vector space is isotropic. Okay? And maximal means that, of course, just maximum. If we just put more vector space, vectors, so that if you want to make one dimension higher, then when this is impossible, we say this, of course, maximum. And what we know is that any maximal isotropic subspace in here is n dimensional. So this means that this should be the n dimensional. So these two n indicate that this is lying in the two n dimensional ambient space, and this n indicate that this is indeed n dimensional vector, the set of the n dimensional vector spaces satisfying certain condition. This O stands for the orthogonal. Okay, this is called the orthogonal Grassmannian.
So is that true that x and x are orthogonal in this sense?
Yeah, so x should be 0. Yeah.
So what does this mean? Like, so is
Ah.
there intuition of what vectors satisfy this?
Okay, so let's give you one example in respect to regarding those. So here, let's consider some 2n vector space. So here I put I will consider our vector space in terms of the matrix. Okay, so taking the row space, then we may consider B. And here, so this part is the identity matrix. So the columns are labeled by 1 through the n, and this part is some n by n matrix, which row columns are indicated by indexed by 1 star to n star. Okay, and V, so our V is row space of the V, taking this as a row space of the V. Okay. And then B is isotropic. So from this definition, this should be the n dimensional because this identity part. And this is isotropic if and only if A is skew-symmetric. So for example, if we consider when n is equal to 2, then if we put the identity matrix on the left-hand side, on the right-hand side, it should be the skew-symmetric matrix. So it looks like somewhat like this. And in this case, I will denote this by x. Then x comma x is equal to the x1 times x1 star. So this is x1 times x1 star. And okay, and also, and x1 star times x1 is just same.
Mm-hmm.
Okay, so this is 0. And x2 times x2 star is 0 times x. So in this case, this is something like 1 times 0 plus 0 times 1 when this I is equal to 1, and 0 times x plus x times 0 when I is equal to 2. This vanishes. Okay. This is the specific case, and indeed, it is not that hard to prove that B is isotropic if and only if A is skew-symmetric.
Maybe you want to show x and y, the second row, first row and the second row. Yeah.
Oh yeah. So first, of course, you may assume that this is equal to y, and because if we denote this by y, and if we take the x and y, then this is 0 if and only if you can easily check this. Since this is equal to x plus y, so this means that y should be equal to negative x. Thank you. Okay, so great. Then with respect to Grassmannian, so there is one very important concept which called the flicker embedding. So this is some kind of way to embed our set of the vector space as some kind of the set of the points in the projective space. So you may parameterize each vector space as a point in the projective space. So way to do that is very easy, just using the determinant. So again, let's starting from the I and N. Okay. And then, so if we take some vector space, and then we may consider this kind of matrix form using the reduced row echelon form, and then taking the all possible maximal minors. So what I mean is that collect all determinant of, I will denote this by the lambda, large lambda, okay? And taking the all determinant of the lambda whose columns are indexed by I for all choice of the I, which is the n subsets of our ground set. So there are 2n choose to n many numbers, and which is just a determinant of the or possible maximal determinant of our vector space, our matrix whose row space is exactly B. Okay. And so this is called the flicker embedding. And one very interesting fact is that this vector satisfies some kind of good relation, which is called the Plücker relation. So I will denote this by PV. Then PV satisfies certain quadratic relation, which is called the Plücker relation. And this Plücker relation is indeed nothing but just kind of cofactor expansion of our matrix A, or the minor or these minors. Okay. And rather than that, let's go back to our previous example when n is equal to 2. Okay. So rather than isotropic case, I will consider some kind of general case. Okay. A, B, C, D. And then our PV is somewhat determinant of those things. And I will denote by this by the delta ij. What I mean is that delta ij is a determinant whose columns are exactly I and j. So for example here, delta 1, 2 is equal to 1, and delta 1, 3, 4 is the determinant of A, B, B, C. So which is A, B minus B, C. And delta 1, 3 is this one. So this is equal to C. And so on and so far. So delta 2, 1, 4 is D. Delta 2, 3 is equal to negative A. Delta and 2, 4 is equal to negative B. And what you can derive from here is that this satisfies certain quadratic equation, which is delta 1, 2 times delta 3, 4 minus delta 1, 3 times delta 2, 4 plus delta 1, 4 times delta 2, 3 is equal to 0. And this is some very specific type of the Plücker relations, which called the three-term Plücker relation, and there are indeed more when n is larger. And so this is some kind of Plücker relation, and I will not give you precise relation of the Plücker relation, but just keep in mind, and you may understand. So vector space can be embedded using the Plücker embedding, and those things are exactly figured out by the Plücker relation. And Plücker relation is some kind of algebraic tool to understand the vector spaces. But in here, we are considering about the isotropic vector spaces. And this is some very specific case. So what I mean is that here, we are just replacing this by the x and x 0, 0, x, negative x. Okay? And because of here, we can find some kind of good relation between we can find some kind of linear relation among those things. So what I mean is here, the delta 1, 3 is in here minus x, and delta 2, 4 is x, right? So yeah, this is just negative of each other. And so what you know is that the orthogonal Grassmannian can be embedded into the projective space of the 2n to n minus 1 dimensional projective space, and this is cut out by the Plücker relation together with some certain linear relation which comes from this isotropic condition. Okay, so this is some half of our story, and at the very first time I will give you some kind of relation between the pfaffian and the determinant, and also we already find skew-symmetric matrix which can be derived from the condition that our vector space is isotropic. So you may wonder that then why I introduced this notion pfaffian, and I will. And indeed, the reason why is that there is another way to embed our orthogonal Grassmannian using the pfaffians. So another way to embed our orthogonal Grassmannian is following. So here we have some kind of Grassmannian, and then we can embed this into the projective space 2n to minus 1 dimensional vector space, projective space using the pfaffian. So rather than that, we consider rather than the vector space, I will consider the n by 2n matrix, and then what you know is that this part is skew-symmetric. Okay, and taking all possible pfaffians of the principal minors, we can embed our space in the projective space. So taking four pfaffians, A, I. So AI means that the principal submatrix whose rows and columns are indicated by I. I is a subset of the power n set, and this is indexed by n and n. Okay. And what we know is that the image. So this is called the weak embedding. And the image of the weak embedding is cut out by the certain also quadratic relation, which is called the weak relation. So basically, weak relation is some kind of extension of the determinant identity. So in the case of the determinant, we have some kind of cofactor expansion. So we can inductively define the determinant from the smaller determinant of the smaller matrices.
Here, what is the definition of AI?
So
subset of n.
So here, A is so this part is skew-symmetric, right? Yeah. And I is some kind of subset of our columns, and so we take the principal sum.
I see. Thank you.
So let's give you some another example. So here we may consider here is identity, and here is 4 by 4, something like A, B, C, D, E, E, F. Okay. And then okay, and let's assume this is skew-symmetric. And the pfaffian of the A is what we know is that AD minus BC plus AF minus BE plus CD. Okay. And Pfaffian of the empty matrix is, by convention, this is equal to 1. Okay? And Pfaffian of the odd size submatrix is always 0 by definition of the Pfaffian. And Pfaffian of this, which is indexed by 1 and 2, so that we consider this submatrix. Then this is equal to A. And so we have some 6 different choice of the I and J, and these are just depending on I and J, this is B, C, D, E, F. And if we denote this by something like W, then what we have is W empty times W1, 2, 3, 4 is equal to W1, 2 times W3, 4 minus W1, 3, W2, 4 plus W1, 4 times W2, 3. So still, we have some kind of weak relation. And I will not give you the precise definition of the all possible weak relation, but if we collect all possible weak relation, and indeed it uniquely determines our original vector, isotropic vector, maximal isotropic vector space. So in a big picture, we have 2 embeddings of orthogonal Grassmannian. So one is from the applicable relations, and the other comes from the weak relation, weak functions, weak embedding. So which is embedded in a 2n choose n minus 1 dimensional space, and this is embedded in the 2n minus 1 dimensional vector space, projective space. However, this weak embedding is defined in terms of the Pfaffian, and the previous one, Plücker embedding, is defined in terms of the determinant. And we already know the kind of relation between this determinant and the Pfaffian. And so what we know is that indeed we can find some kind of good bijection between those two. More precisely, we do not know all information of here. So indeed, it suffices to consider some kind of specific minors of our matrix, skew-symmetric matrix A, rather than taking the all possible minors. So passing through the restriction by so that we may consider 2n plus n minus 1 to 2n minus 2 minus 1. And indeed, each coordinate indicate the principal minors and the almost principal minors at our skew-symmetric matrix. And so we give some kind of good relation between this from the Cayley's Pfaffian identity. Okay, so we have some kind of 3 equivalent notions. So we have some kind of maximal isotropic vector space, and you may understand this as some kind of point in here which satisfies the weak relation, and or we may consider we may identify this as a point in this projective space which satisfies some Plücker relation together with a certain linear relation comes from this isotropic condition. And our main theorem is that indeed we generalize this concept in a more broader sense. What I mean is defined over some hyperfield or partial field or some more generally trace. So our main theorem is that or a track. I will give you definition of this a little bit later. But if you already took my talk in the kiosk workshop, then you may remember. So. Okay, I don't believe this is quite complicated, but whatever. Yeah, then let's try to explain those. There are natural bijections. The first one is orthogonal F. Which is also which is some kind of projective equivalence class. with function. And the second one is also the projective equivalence class. Let's just say equivalent classes of restricted Grassmann-Plücker is GP for the Grassmann-Plücker f functions. And the last one is orthogonal f signature. So you may guess from the name that the first one generalized the concept in here. Okay, this is one, and the second part corresponding to there. Okay, defined by the Plücker relation, and the last one is some kind of concept generalizing the maximal isotropic vector space. And here you may wonder that what the hell is this? So what is the track, and what is the orthogonal matroid, and what is everything else? So let's roughly speaking, a track is some kind of general notion generalizing the field. So in the case of the usual field, field is always very good, but in some sense this is not good. What I mean is that in the case of the field, it is hard to consider some kind of morphism between fields. What I mean is that morphism between fields are usually very trivial. But if we just consider some kind of more generalized concept, and morphism is still extent of morphism of the field, but we can find some more, kind of very interesting result from those morphisms. And
what is this second line, the last word in the second line?
Last word in the second line. F.
Okay, line labeled number 2.
Here?
Yes.
F functions, sorry.
Functions, sorry.
F functions. Yeah. So yeah, this is concept of some kind of generalizing the field, and some interesting example of the track is some kind of very specific hyperfield, or some kind of very specific partial field, and their representation over for the matroid over that specific track just corresponding to the regular matroid, or some kind of evaluated matroid, or oriented matroid, and also those kind of concept can be generalized in terms of the orthogonal matroid. So orthogonal matroid is a concept generalizing the matroid. So usual matroid is for the linear spaces, and this orthogonal matroid is for this maximal isotropic space. And you may consider, so maximal isotropic space has more condition than the usual space. So why this is more general? But you may consider, if you start some kind of vector space in Kf, and then you may consider some direct sum together with its orthogonal complement, then it naturally satisfies our symmetric bilinear form. So you may understand this vector space itself as by identifying this together with this pairing, and then you may understand this as a maximal isotropic space. And this is very specific maximal isotropic space, and so by generalizing those kinds of concepts, and you may consider maximal isotropic vector space is some kind of generalization of the usual linear spaces, and those kind of correspondence, or you can commenter understand as a kind of commenter understand matroid can be generalized as an orthogonal matroid. Okay, so this is our main result, and let's give you some kind of introduction about the tracks and some orthogonal matroid. Why this is our interest. Starting from track. which was introduced by Matt Baker and Nathan Bowler. A track is a pair of a multiplicative monoid. Which has an identity element and some absorbing element. So of course, identity element means that if you multiply 1 together with any other element x, then the resulting element is x. And zero absorbing element means that 0 times x is always z. Okay? And so this is one part of this track, and one another part is some kind of set, which denoted by NF, which consists of the former sums of the non-zero element. One another way to understand is NF is a subset of the semi-ring generated by the non-zero element. So here fx denotes just nothing but f minus our unique absorbing element just. Okay. So yeah, what I mean is that you may understand element in here is like 1 plus x plus y plus 1 plus and so on and so forth, okay, with a finite number of the terms. And
Here sum means it is commutative, right?
yeah, yeah, thank you. Yeah, so this is commutative, yeah, formal sum. Yeah. And together with certain axioms, which satisfy the 5 axioms. The first condition is about the our multiplicative operations. So fx is an abelian. And the second condition is that 0 is in NF. Okay, beforehand, I will usually call this, people usually call this as the null set. So you may understand this as a 0 set, the sum to be 0. Okay? So NF, so 0 is in the null set. And any other non-zero element is not in the null set. And the third condition is that if you have some kind of element in our null set, and you have some non-zero element, and then it naturally acts on the NF, so that summation of this CAI is also in the null set. So before go, okay. I will give you some example after introducing the whole axioms. And the first condition is that if you have some kind of, okay, so first condition is that if you have some kind of sum in 2 different sums in the null set, and then their summation is also in the null set. Which is sum to 0 and sum to 0, then everything sum to 0. The last condition is some kind of about the inverse, additive inverse. So in the multiplicative notion, since this is abelian group, we have already inverse element, multiplicative inverse, and here we have also additive inverse as well. What I mean is there exists a unique element, which usually denoted by -1, such that 1 plus -1 is in the null set. Okay. And one easy corollary, one easy lemma about the track is that if f is track, then one you can check is that scale of the -1 is equal to 1, and another condition is also another very good observation is x plus y is in the null set if and only if y is equal to the negative 1 times x. Usually this is denoted by negative x. Okay? Okay, so definitions are quite complicated, but let's give you some examples. And so of course the most basic of example of the track are fields. You may understand every field as a track in the following way. So K field. Okay. And then, so you may understand our field K as a track. Okay. And here we naturally have some kind of identity, multiplicative identity element, and absorbing element zero. And so Kx is the usual non-zero set of the non-zero elements. And the important thing is that then what is Nf, which satisfies those conditions? And if we take our Nk as just the set of the all formal sums, which sum to 0 in K, then it satisfies those actions. Formal sums of the non-zero elements such that which is 0 in K, then this satisfies those actions. So the first condition is non-zero element is abelian group. That's one axiom of the field. And second condition, 0 is in the null set here, and every non-zero element, of course, is not in the null set by definition. And also, you may check the remaining conditions as well. So yeah, those notions are generalized in the field. But of course, I should introduce something more. Otherwise, it is not that interesting. So let's give you some other interesting examples of the track. Say example 2. So this board K. This is as a set. This is just consists of 2 elements, and which call the Grassmann field. And each null set is defined as the following: 0 and 1 plus 1 and 1 plus 1 plus 1 and so on and so forth. So everything, every formal sum of the non-zero element except for the just single element. And somewhat trivially this satisfies those conditions. But the importance of this Grassmann hyperfield come when you understand this 1 as a just set of the non-zero elements. Okay. So here let's understand. When we start, let's starting from R, and we divide our R into 2 classes, which is just 0 and non-zero element. Okay. And 0 stands for the 0, and 1 stands for the non-zero elements. And what we know is that possibly some of the two non-zero elements can be 0. And those kind of things can be observed from our null set of the Grassmann hypothesis. 1 plus 1, non-zero element plus the non-zero element can be 0. And non-zero element plus 3 non-zero element, some of the 3 non-zero elements also could be 0. And maybe another interesting example is the sign hyperfield. I know that some people in this this room or working in discrete geometry and oriented matroid, and this concept is closely related to those things. As a multiplicative monoid, it consists of this just 3 elements, 0 and plus minus 1, and this multiplicative notation operation is defined in a usual way, and this is called a sign. So this plus 1 and the minus 1 indicate the sign or the all possible non-zero elements. So now we divide our R into the 3 sets. So 0 and all positive numbers and all negative numbers. Okay, and you may understand this positive number as +1 and the set of the negative number as -1. Okay, then our null set consists of some very different sets. So it starts from 0, and here 1 plus 1 is not in our null set because positive number plus positive number cannot be 0. But in contrast, 1 plus negative 1, positive number plus negative number can be 0. So by collecting all possibility, you may understand this as a null set of our sign hypothesis.
So 1 plus 1 plus minus 1 is in both sets.
Yes. So all possible formal sums with the 3 terms are 1 plus negative 1 and 1 plus negative 1 plus negative 1 and so on and so forth. Thank you. Great. And yeah, one interesting thing is that Grassmann hyperfield is a final object in the category of the track. I didn't give you the definition of the morphism of the track, but interesting thing is this is some kind of final object. And this is, of course, not a final object. However, what we know is that there is always a morphism from the R to S, and more generally, we can replace this R with any ordered field. And this gives us some kind of interesting observation in respect to matroid theory or some kind of theory of the orthogonal matrix. Okay, so yeah, so what I want to introduce is we can understand those kind of concepts with the rather than the field with the more general concept like Grassmann hyperfield or sign hyperfield or something else. Another example, what I like is the regular partial field, which is the initial object of the category of the track. So as a multiplicative monoid, this is same as the sign hyperfield, but its null set is somewhat very different. This is just 0 and 1 plus negative 1. However, there is no formal sums with the 3 terms, but its next term is 1 plus 1 plus negative 1 plus negative 1. So we collecting all formal sums which sum to 0 in the integer ring. Okay, and this pair is called the regular partial field. And this is category of this is initial object and an orthogonal F1 F1 plus minus matroid. So representation over the regular partial field corresponding to the some kind of regular delta matrix, just same name. One another way to express this. And using those kind and indeed we developed such kind of theory. Oh, wait a moment. So here I just forgot to mention that some important thing in here. So here, in our main theorem, we introduced the second notion, and we show that equivalence between the other concept. And those two concepts are introduced in my early paper with Donggyu. So those two notions are introduced by with Donggyu, and indeed that paper we introduced the equivalence between those two. And in this project with Changxin, we proved that those kind of things. There is some kind of good map from the 1 to 2 and 2 to 3, so those are notions are the same. Okay. Mm-hmm. And one thing is that, so I and Matt Baker and Changxin Ding and me, using those kind of theory, we using the some kind of orthogonal method over the regular partial field, we study some kind of algebraic properties of the ribbon graphs which gives some kind of very interesting some kind of group actions on the Jacobian group to the some kind of set of the all possible spanning quadrics, and which is very natural example of the orthogonal method. And okay, so in the remaining 5 minutes, I will try to introduce some kind of notion of the orthogonal method, and I will try to convince you why orthogonal method is interesting concept. So here, so I introduced, I starting from the some kind of linear algebraic thing, and I define some very weird thing. And here you may find some terms which called orthogonal metric 2 times here and there, and many more. Okay. And the reason why is that to define this over the hyperfield or some kind of general notion, it is some kind of unavoidable to giving you to assume some kind of underlying combinatorial object. Without this, it is quite hard to understand. So, and to do this, we should consider the orthogonal method, and this we also call the even delta method. And here, let's briefly give you the definition of the orthogonal method in terms of the even delta method. Maybe Sang prefer to use this notion, but yeah, but sometimes it is better to using its homogenized version, which is called orthogonal method. But I will give you. Let's do it in terms of orthogonal method. So
I mean, your curve was like that word.
that's good. Okay, I didn't heard.
Yeah, you
okay. So let's give you some definition of the even delta method and give you some kind of very interesting examples. Okay. So here in even delta method, and this is some kind of pair, which is finite set together with some set of the subsets of our E. Okay. A set system on even delta method. If first our collection of the set system, this is non-empty, and the element in here called the basis, okay? And the second condition is some called the basis exchange action. Which is the following. So you have two bases. And then also you have some element in their symmetric difference. Then you can always find some another element, F, in the symmetric difference, such that by exchanging those two elements, we may obtain two other bases. And one easy lemma is that if you have even delta method, then all bases have the same parity. Okay? And matroid is some kind of specific case. So when our bases have the same size, then this is precisely the matroid. Okay? So you may define matroid in those sense. And so this is some kind of concept generalizing the even the matroid, and orthogonal matroid is some kind of homogenized version of the even delta matroid. What I mean is that possibly there are many different bases of the many different sizes. Okay. However, if you rather than let's denote our ground set by 1 to the n, and then we may double our ground set. So let's do it. Rather than that, we may consider our ground set with the n with the n star. So there are two n elements. So it means 1 star, 2 star, and so on, n and n star. And for the basis, for each basis, rather than this, you may convert this into the B union and delete B together with some star. Okay. just attach star for the each element in this complement. And this has always n subset, size n. And you may consider some, so by lifting our each basis, you may consider some kind of homogenized version of the even delta matrix. And this pair, set of all, by collecting all of those, and you may consider this pair is just exactly the orthogonal matrix. And this is some kind of homogenized version. And there is some kind of good things in when we're working on the orthogonal matrix rather than the even delta matrix. But I will skip to doing that. Okay. So one good thing is that the circuit is defined in a very natural way. Okay, let's finish with some examples of the even delta matrix. Okay. Example. Okay. So example 1. Let's starting from some graph. Okay, finite graph. I'm happy that Pascal is not here since I won't want doing some for over the finite graph. Okay. So finite graph. So and then our ground set is equal to the set of the vertices. Okay. And then our set of the bases is some set of vertex sets, which precisely covered by some matchings. So match over. What I mean is, for example, our graph looks like this, which indexed by 1, 2, 3, 4, and then the vertex set 1, 2 is matchable because of there is some kind of matching, and also 1, 2, 3, 4 can be matchable because 1, 2, and 3, 4. Okay, such kind of example, and because of some kind of argument past argument, you can easily check that indeed this is an even delta matrix. And second example, what I like is about the ribbon graph. So ribbon graph. Which usually denoted by this blackboard G. And okay. So you can starting from some graphs, okay, which looks like this. So 3 vertices and 3 edges, and with 4 edges, and together with some 1 loop edge. Okay. And in this case, which is planar. Planar. And there is some kind of way to understand this as plane graphs. It's just same way. However, so after taking the plane embedding, you may thicken our edges. So thicken our vertices as some kind of small disk, and you may thicken our edges in a small band with the small band. However, you may embed this graph in the torus. And then, so what I mean is, so you may embed our vertices here, and then edges looks like this one. And in those way, you may draw our graph in those way. So basically, ribbon graph is some kind of notion which has some kind of additional topological data, and this is this is closely related to the knot theory or some kind of graph with the vertex and the pivot minors. Okay? And in here, there is some notion which is called the spanning quasi trees. What it means is you collect all edges which give one single boundary component. So what I mean is here I will try to denote this by the 1, 2, 3, 4, and then if you collect, if you take these four edges, 1, 2, 3, 4, then interestingly, that this has a unique, this has a single boundary component. Okay. So spanning quadrilaterals of here is just 1, 2, and 1, 3, 2, 3, and 1, 2, 3, 4. So rather than it, of course, it contains all spanning trees and together with some additional things. And if you collect all those kind of edge sets, then it also forms the delta matrix. And I will give you, because of the lack of the time, I will do not give you the definition of the representable delta matrix, but it just comes from the skew-symmetric matrices. Okay, and those two examples are example of the representable delta matrix, and this is representable over the very large field, depending on the graph, and this is representable over any kind of field. And yeah, so our main theorem is somewhat do not have a right immediate application, but we somewhat believe that maybe some give another understanding of the orthogonal method with the coefficient. Maybe there is some kind of good application in the future, maybe. So, okay, so this is the end of my talk, and thank you for listening.
All right. Questions? Any questions?
So Peter Nelson has this theorem that almost all matroids are not representable.
Oh yeah.
Is there something like this for
Yeah.
orthogonal matroids and tracks, I guess?
What's your guess?
Should be that.
Yeah, should
most-
be. Yeah,
most
there
of
there
them-
is there. Yes, as you expected, there is, and indeed, Donggyu and my current boss Matt Baker proved that there is exact analog chord as well. Yeah.
My question may be a bit silly. So in the Kias workshop, you're talking about polymetroid
Mhm.
and their representation, and today you're talking about orthogonal metroid and their representability.
Yeah.
But is there any relation between those two concepts?
So their common intersection is a metroid, and metroid coefficient is some kind of concept. And as I said to you, that polymetry is some kind of multi-set version. So this is some kind of another way to generalize the metroid. And in my opinion, so the two best generalization of the metroid is one is polymetroid and the other is orthogonal metroid.
So there is some kind of different direction.
Yeah,
of
different
generalization.
direction. And there is also common generalization as well, but I think that part is not well studied yet. Which called the jump system with some parity condition.
Any other questions? If not, let's thank the speaker.